Dear learners, welcome to yet another video on Green's theorem. This video is different from this problem is different from the earlier problems we have discussed in two aspects. The first one is the previous two problems are on verifying Green's theorem. So we have to evaluate both the left hand side and right hand side to verify the Green's theorem. But this problem is to evaluate the given integral, single integral, using Green's theorem. That means we know that the Green's theorem is the transformation from double integral to single integral and converse. So here the single integral is to be evaluated as a double integral. The question is not to verify, so it's enough if we evaluate the double integral alone. So first, before proceeding with the problem, the basic aspect, we sketch the region of the integration. So x square equal to y is a parabola and y squared is equal to x is also a parabola. So the region bounded between them is as shown in the screen. Now it's our aim to get the points of intersection. So to get the points of intersections, we note down the equations of the parabola y square equal to x and x square equal to y. Solving these two equations simultaneously, from x squared equal to y, we get, substituting in the first equation y square equal to x, we get x power 4 minus x equal to 0. So grouping the terms to one end, we get x into x cube minus 1 equal to 0. So x is equal to, on equating x equal to 0, we get x equal to 0. On equating x cube minus 1 to equal to 0, we get the cube roots of unity 1 omega and omega squared. But considering only the real roots, because we are on the real plane and it's a real integral we are discussing with. So considering only the real values, we get x equal to 0 or x is equal to 1. So substituting in any of the two equations, x square equal to y and y square equal to x, we get the points of intersection to be 0, 0 and 1, 1. So now let's recall the statement of Green's theorem. So if R is a connected closed region, that is, it's a domain that connect, and f1 and f2 are continuous, and the partial derivatives dou f2 by dou x and dou f1 by dou y are also continuous in the domain that contains the region R, then we have integral over C f1 of x comma y dx plus f2 of x comma y dy is equal to dou f2 by dou x minus dou f1 by dou y dx dy. Because this is not the process of verifying the Green's theorem, it's just evaluate. So given the line is single integral, we are going to perform the equivalent double integral. So f1 is as given in the question, x squared 3x squared minus 8 y squared dx plus 4y minus 6xy dx dy. So differentiating, evaluating dou f2 by dou x and dou f1 by dou y and substituting in the integral. I think I have made a mistake here. So dou f2 by dou x is minus 6y. So carrying over the corrections, we have 16y minus 6y, which is 10y dx dy. Now to evaluate the double integral over R, we have to take either a horizontal strip or a vertical strip. Here we consider the horizontal strip. So taking the horizontal strip, it starts from the parabola y square equal to x and ends on the parabola x square equal to y. So our and the strip starts at the starting point, we have x equal to y square, and at the end point we have x is equal to root y. So we have x varies from y square to root y, and we have to move the strip from y equal to 0 to y equal to 1 to cover the entire region. So y varies from 0 to 1. So the double integral over R 10y dx dy takes the form 10 into integral 0 to 1 integral y square to root y dx dy. And from the order of integration, first we evaluate with respect to x. So 10 into integral 0 to 1 x y square to root y dy. On applying the limits, it is root y into y. On applying the upper limit, we have root y minus y square, and into y we have in common. So root y into y, it is y power 3 by 2, and minus y into y, it is y cube dy. So integrating y power 5 by 2 by 5 by 2 minus y power 4 by 4 under the limit 0 to 1, and applying the limits we have 2 by 5 my 10 into 2 by 5 minus 1 by 4. So on taking LCM, it is 10 into 3 by 20, so which is 3 by